Hi there, welcome back to the Renewable Energy Technology course. I am Miro and we will talk about wind turbines. This is the first lecture out of a series of 3 lectures on wind turbines. Let me remind you that we actually concentrate on the turbines, mechanical construction, aerodynamics and engineering, not on the wind resource and not on too much soft issues. We will look at the second section of the first lecture today, and that would be the fundamental theory of wind energy conversion. How exactly we can extract energy from the wind. There are 2 basic conceptual limits. 2 very important conceptual limits. The first one is the fact that by taking energy out of a fluid flow, we cannot completely stop it. The fluid should continue flowing behind our energy conversion device. So this means that we cannot decelerate the fluid down to 0 or extract all the velocity from it, because we're actually extracting kinetic energy. It should continue flowing. The second reason is that the energy conversion device, and it doesn't matter how it looks like, actually is obstructing the fluid flow. It is a kind of an obstruction to the fluid. And there is nothing that tells us whether or not the fluid would really pass through our device. Maybe it would bypass it. And that's exactly what happens in reality to a large extent. If we look at a simple but good enough drawing that can serve the needs for proving this concept, our energy converter would be sitting right here. Again, it doesn't matter, absolutely not, how it looks like. It is not important whether it's a turbine, a rotor, or a vibrating disc, or a flapping sail. It can be anything. The fluid comes from the distance and approaches our energy converter, after which the fluid continues flowing. What happens is that some of the fluid really bypasses the energy converter. And you can think of this as if you're ramming the wind with a flat front truck, for example. There is a large flow actually going around, escaping the solid object. Even if you try to use that flow to pass through your object, still some of it would bypass it. We define 4 important points. The first one, far ahead of our energy converter. The 4th point, again, far behind our energy converter. These are actually, at point 1, the undisturbed fluid, the most important point. At point 4, the ideally disturbed, let's call it so, fluid, while points 2 and 3 are assumed to be infinitesimally close to each other. They are supposed to lie just in front and just behind the energy converter. It's impossible really to show it on the figure, but just imagine that the energy converter also is actually now invisible here, while points 2 and 3 are immediately in front, immediately behind it. The important physical conditions, first of all, that the velocity doesn't change abruptly. Velocity falls gradually throughout the zone where the device is affecting the fluid flow, while the pressure is building up just in front of the device and then decreasing behind it. The pressure at point 1 and the pressure at point 4 is the undisturbed atmospheric pressure, the governing pressure for that location. While exactly at points 2 and 3, a pressure differential would build up. And this is exactly the fact or the force forcing the fluid to bypass the device, or also forcing some of it to actually pass through the device using this pressure differential. There are also some important simplifying assumptions. First of all, the flow is homogeneous, incompressible, slow speed, and steady state. There is no time perspective here. There is no friction, no boundary layers, absolutely nothing. The energy converter is ideal and is of no specific nature. It doesn't matter for this theory how the energy converter looks like, whether it rotates or whether it does something else. The flow is uniform. and the forces are uniform throughout the area. And most importantly, the flow is one-dimensional. There is no turbulent wake behind the energy converter. And this is what we use to call the one-dimensional momentum theory. Actually, these simplifying assumptions, not only that they are important, but there are no limitations. They actually define the best case. They define the ideal situation that we will now try to derive the theory for. Any reality, any real condition that we would, as usually done while proving such things, adding it further after the ideal conditions are being defined, any real case scenario would actually introduce a loss. So by defining these simplifications, we actually define the best, the most ideal, the most performing case. Using conservation of linear momentum, basic classical physics, the thrust, that is the force that the fluid induces on the rotor or on the energy converter, to be impartial, is the pressure difference multiplied with the area of our energy conversion device. So we would need to describe somehow how much this pressure difference is. At the same time, the thrust also is the mass flow multiplied with the drop of velocity. This is exactly what converts energy or extracts power from the fluid, the drop of velocity. We can use Bernoulli's relations for the areas where there is no work being done or no energy being extracted. This is between points 1 and 2 in front of the rotor and points 2 and 3 behind the rotor. Bernoulli's equations actually show a balance of pressures. And remember that this here also has a dimension of pressure. We can work with those two equations and actually represent with them exactly the drop or the pressure that builds up across the energy converter. And it is a function of the velocities of the fluid far before and far behind the energy converter. The mass flow, though, the real mass flow that actually passes through the energy converter, is defined by the velocity at point 2, which we don't know and probably cannot even measure, so we'll try to represent it with something else. Working with the equations that we already have, we actually can extract the velocity at point 2 and see that it's a function of those velocities of the fluid far before and far behind the rotor. It actually is the arithmetic average of the velocities at point 1 and point 4. Very interesting result. And this is, let me remind you again, this is the best case. Then a specific component is introduced to help us mathematically work with these equations. It is usually called the interference factor, and that name is most descriptive because actually it represents the ratio of how much the speed decreases from point 1 to point 2 related to the undisturbed speed at point 1. Most often actually in literature you can see this as, or denote it as, axial induction factor. It says the same thing, so how much actually the flow induces something to the energy converter by slowing down itself. We can use this artificial component to actually represent with it the velocity at point 2 and the velocity at point 4 as a function of the axial induction factor and the most representative velocity at point 1, the one that we can measure. Then the power is actually a product of the thrust force, the force that the fluid induces on the solid object, times the velocity exactly at point 2 at the energy converter. And we see that it's a function again of velocities. Of course, it depends what the density of the fluid is and what is the area that we consider. We can convert the equation for the power output into this final form. And it's easy to see that here we have the energy contained, or the power, in the undisturbed fluid. while this remaining part of the equation is something that maybe represents how efficient our device would be. So we call it a power coefficient. The power coefficient is exactly the ratio of the actually converted power, or the possibility to convert power from the flowing fluid, related to the available, the contained power in the fluid. So the CP, the power coefficient, is exactly this function, a cubic function of the axial induction factor. We can work with it, basic mathematics, and extract the first and second derivative to find out that it actually has an optimum when the axial induction factor is 33%, 1/3. And the optimum is indeed a maximum, which in numbers is exactly this number, 16/27, approximately 59%. This, in fact, is the maximum possible at any condition. This is the best scenario, conversion of power from a moving, unrestrained, free-flowing fluid into mechanical power. And that would be the maximum possible one expressed in figures. Albert Betz, a German physicist, was the first one to actually publish these results and to derive it in this way in 1926. CP represents the maximum ideal, let's be very careful now with the words here, aerodynamic efficiency of possible energy conversion from a free-flowing, unrestrained fluid stream. And it doesn't matter what kind of device actually converts the energy, it doesn't matter what kind of fluid we talk about, whether it's air or water, where the device is submerged in water without any casing, without any channeling, or if it's honey or molten gold, this theory holds. How do we interpret the Betz limit? The Betz limit very nicely shows what will happen with the flow if we extract the best or the most power from it. There was also a British multi-engineer, Frederick Lanchester, who actually worked on this and tried to derive it before Betz, but he got stuck really with the mathematics because he tried to make it much more complicated, while Betz really followed the direct path of proving the most really ideal case. And in that case, if our energy converter is sitting here, we can call it in different ways, it doesn't matter how it looks like and what it does, it actually affects the flow in a way that some of the flow bypasses the converter, and indeed only a part of it is the one that actually goes through our energy converter. In terms of values, 1/3 of the available energy in the fluid will bypass our energy converter. We are losing already now 1/3 of the entire energy of the fluid. 2/3 is really passing through the device. In the best case, it would convert 16/27 parts of that available energy. And behind it, there would be only 2/27 parts of the available energy in the fluid left in the wake behind the energy converter. So the wind continuing to flow behind the device, and it has to continue to flow and leave room for other wind coming, would have 1/3 of the initial velocity left in it. You see, it's not much slowed down. It's 33% of the velocity is still there, but it's not much in terms of energy. It is only 2/27. This is less than 10% of the initial available energy left in the wake. There is not much really energy to extract there. The device is pretty efficient, even if only 16/27 parts have actually been extracted. That is approximately 59%. And the ideal speed at point 2, exactly at the device, would be 2/3, 66% of the initial speed. The power coefficient actually is applied to represent the typical aerodynamic efficiency of our energy converter. In reality, the actual CP would be far less than the maximum possible due to, well, the real case where any other losses are being added on the ideal scenario. So in reality, the real output in terms of power for any energy converter would be represented by the available power in the wind, multiplied with any aerodynamic efficiency hidden behind the CP concept, any other kinds of mechanical losses, and any other kinds of electrical or different types of losses. CP should not be confused with the very common COP index, the coefficient of performance used in the refrigeration industry. CP is purely linked to aerodynamic efficiency. And even if the coefficient of performance also has the meaning of efficiency, it has nothing to do with the power coefficient used in turbines. There is a thrust coefficient that can also be defined and used, however, not for expressing efficiencies, but simply representing the ratio of important or less important forces on our solid structure. So when it comes to real devices extracting energy from a flow, the thrust coefficient would probably show how much forces those devices will have to withstand. The CT, that is the thrust coefficient, should not be confused with CP. It has no meaning in terms of efficiency. The CT and CP are, however, related because if we look at now the best performance possible for any kind of energy extraction device, and if we use some kind of a typical drawing now representing the function of CP as a function of axial induction factor and CT by itself also, this line here would be the ratio of the very much disturbed velocity behind the rotor and the undisturbed velocity, starting from 1, no disturbance, and going down to 0, where the flow is completely stopped, where the theory actually loses its meaning completely. CP, the aerodynamic efficiency, the power coefficient, would be maximum at the axial induction factor of 1 related to 33%. And it will be 59% or 0.59 in terms of its actual value. At that exactly point, the speed of the velocity of the fluid would be 33% of the initial one. The thrust coefficient, however, grows constantly. And the more efficient you see our turbine is, the more forces it would need to withstand. And the thrust coefficient can much easily be remembered or logically linked to actually how efficient, again, our rotor is. Now, if it is really a turbine rotor extracting energy, if we don't take much energy from the fluid, we wouldn't change much the fluid streamlines here. You imagine that. If our rotor is more efficient and more productive, taking energy from the fluid, we would have a big influence on the flow of the fluid. And of course, our device will need to withstand much higher forces in order to handle its performance. So what we managed to prove today was that the ideally best performance of a single stage wind rotor, it doesn't matter how it looks like really, is a maximum of 59%. It is not possible to extract more energy from a moving fluid flow if it's not restrained. We call this the power coefficient. And in real life, the power coefficient would be somewhat less than the maximum possible power coefficient, usually far less than 59%, than the maximum possible. Any kind of real life scenarios or adding additional realities to this very basic simplified theory would actually add losses and inefficiencies to the performance of the real actual turbine. Thank you. Yeah.